Good morning, everyone. So, welcome to my YouTube channel, Maths Saptaram. So, today we are going to see fourth practice set on functions of bounded variation. So, let's start today's session now. So, first of question is given: f be a function of bounded variation on closed interval AB. Which of the following statements is correct? First is if f is differentiable on closed interval AB, then f is function of bounded variation. Okay. Second is if f is continuous on closed interval AB, then f is function of bounded variation. Third option is if f is Riemann integrable on closed interval AB, then f is function of bounded variation. And fourth is none of the above. Okay. So let's see this solution of this question. Okay. Now, first option is not correct. If function is differentiable, it need not be a function of bounded variation. You see this example. X square sine 1 upon x square. X belongs to open interval 0, 1. We will show that this function is not function of bounded variation. This is the last question in our practice set. Okay, we will show there. And it is 0 if x is 0. So you see that this function is differentiable everywhere. We need to check only at x is equal to 0. So f x is equal to 0. What is this? F dash at 0. So this is x square sine 1 upon x square, okay, minus 0 upon x minus 0. So after solving it, what you will get? This is 0. Okay. So if x is not 0, then f dash exists. Okay. If f is 0, it also exists at x is equal to 0. This implies f dash exists. But f is not function of bounded variation. Okay. We will show it why it is not function of bounded variation. This is the fifth question in our practice set. Okay. So first option is not correct. Second option is not also correct because every differentiable function is continuous. Okay. So this function we have taken now is also continuous, but it is not function of bounded variation. Third one is Riemann integrable function. We know continuous functions are Riemann integrable. So this function is also Riemann integrable, but it is not function of bounded variation. So all three options, first three options are not correct. It means none of the above. D option is correct. Okay. So f be a function of bounded variation. Which of the following statement is correct? There exist unique positive monotonically increasing functions P and Q such that f minus f is equal to P minus Q and Bf is equal to P plus Q. Okay. Second option is there does not exist positive monotonically increasing function P and Q such that F minus F is equal to P minus Q and DF is equal to P plus Q. Okay. And C option is there does not exist monotonically increasing function P and Q such that F is equal to P minus Q and DF is equal to P plus Q. Option C cannot be correct because by Jordan theorem such functions monotonically increasing functions exist whose difference is F and sum is DF. Okay. So option C is not correct. We need to check option first whether there exists such monotonically increasing positive function such that F minus F is equal to P minus Q and their sum is BF. Okay, we will check it. Okay. Okay. So I can write by Jordan theorem. There exists P is equal to BF plus F. They are unique. There exists unique P and Q. Monotonically increasing. Such that F is equal to P minus Q. Okay. But I can write F minus F is equal to P minus F by 2 minus Q plus F by 2. Then what is this? Then what is this function? This function is BF plus F minus F by 2 and this is BF minus F plus F by 2. Okay. So let's say P naught is equal to BF plus F minus F by 2 and Q naught is equal to BF minus F plus F by 2. Now, this is because F is constant, so this is monotonically increasing because BF plus F by 2 is monotonically increasing. Because BF plus F by 2, I can separate it by F2. I can write it BF plus F by 2 minus Fk by 2. Because these functions are monotonically increasing and this is constant. So finally P naught is monotonically increasing. Similar here, this is monotonically increasing, this is constant to monotonically increasing. Okay. Now, if we can check at initial point they are 0, then this will be positive function because it is monotonically increasing. So let's check it. P naught A, what is this? BFA plus Fk minus Fk by 2. Now this is cancel out. So BFA by 2, but BFA is non-negative function. Sorry. BFA is 0. So this is 0. But P naught X is monotonically increasing. So this means this. It means P naught is positive. Okay. Now similarly Q naught X is greater than Q naught A. What is this? BFA minus Fk plus Fk. by 2, but this is cancel out. This is BFA by 2, that is non-negative, that is 0 actually. That is 0. That is 0. This implies Q naught is positive. Okay. And F minus FP is P naught minus Q naught. Okay. Now, BF we know that adding the constant. So BF, so if we have any constant, if you add any constant, then variation do not change. Okay. If you will add in any constant in any function, the variation will not change. So what will the variation of F minus Fk? This will be equal to variation function of F. Because variation do not change adding a additive constant. So it is equal to this. So this implies BF is equal to P naught plus Q naught also. And why this is unique? Okay. P naught and Q naught are unique. Why? You add P naught and Q naught are unique. Because you can add, let's say equation number 1, add 1 and 2. We get, what we get? BF plus F minus Fk to P naught. So this will imply P naught is equal to 1 by 2 BF plus F minus Fk. Okay. And if you subtract 1 and 2, 2 and 1, we get, what we get? BF minus F plus Fk is equal to 2 Q naught. That implies Q naught is equal to 1 by 2 BF minus F plus Fk. Okay, so this implies P naught and Q naught are unique. Okay. So which option is correct? First option is correct. So first option is correct. There exists unique positive monotonic integer function P and Q such that F minus F is equal to P minus Q and DF is equal to P plus Q. Okay. So now let's see third question on it. Let F be a function of bounded variation. Consider the function G such that G is equal to 0 and Gx is equal to 1 upon x minus a. Integration a to x f of dx for x belongs to a. Then G is not function of bounded variation. G is unbounded. G is function of bounded variation. None of the above. Let's check it. First of all, we know that there exists P and Q positive monotonically increasing functions such that F minus Fk is equal to P minus 2. Then I can write it F is equal to Fk plus P minus Q. And what is the integration? Gx is equal to a to x fx dx. What will be this? This will be Fk x minus a to x dx dx minus a to x 2x dx. Okay. Now this function is This function is monotone function. So this function is monotone. So this implies it is function of bounded variation. Now we need to check whether this is monotone or this is monotone. If they can be monotone function, the whole function G will be monotone, and monotone functions are functions of bounded variation. Okay. So our problem reduced to check that G1 A at 0 and G1 X A to X Px dx is function of bounded variation or not. Similarly, we need to check this one also. G2 A is equal to 0 and G2 X is equal to A to X to X dx. It is function of bounded variation or not. Okay. So we'll check it. Similarly, G2 can be checked. Okay, we will check only this one. So what is, so let A is less than what is Q1Y minus, sorry, G1Y. G1Y. So G1Y minus G1X. What is this? This is A to Y Px dx minus A to X Px dx. So this is equal to, I can write it A to X Px 1 upon Y minus A will be there. 1 upon X minus A will be there. I can write Y minus A to X dx plus 1 upon Y minus A X to Y Px dx minus 1 upon X minus A to X Px dx. Okay, now combine these two. So what you will get after solving it? So X minus Y upon X minus A upon Y minus A to X Px dx 1 upon Y minus A X to Y Px dx dx. Okay. Now Px is monotonically decreasing, so I can take initial point and I can change the variable. X minus Y, X minus A, Y minus A to X Px dx. Okay. So I can change the variable here. I can write t here, no problem, because it will not affect anything. I can take t here. Okay, but t is monotonically increasing. So if I will take initial point, this will be less than equal to, I can take initial point here inside. integration, because this is monotonically increasing. So this will be less than equal to. Okay. Okay. So what is this? After solving it, what will Px will come out? This will be y minus x upon y minus a Px. Okay. So I can multiply by x minus a. Then what I will get? What I will get? X minus y upon x minus a, y minus a, a to x minus pt minus okay. Sorry, 1 minute, 1 minute. I can take px here, but this is monotonically increasing x to y. I have breaken x to y, and this is px, and this is y. So since this is monotonically increasing, okay, so I can put here PA also. I can put PA here, PA. Okay. So this is monotonically decreasing. It is PA here. So this is, after taking common, this is PA minus DT. Okay. So what is this? PT minus 1 minute. Let me check it again. So I put this one is equal to A to X. I combined this, and this is nothing but this X to Y. X to Y I can write X. Px I can write okay. So I can write it A to X. Sorry. Sorry. I can write Px here. Sorry. Px. Because this is monotonically increasing, taking the lower value, taking the value at lower point, it will not affect anything. So this will be So I am writing again here. So this is Px. I can take Px here. Px. Now, if I will take, you take y minus x upon x minus a, y minus a common, then what will happen? So there will be minus sign here. Minus a to x dt dt. Okay. Now what is this? This is y minus x upon y minus a px. So I can multiply by x minus a upon x minus a. So now you take this thing common, y minus x upon x minus a upon y minus a. Then this will be what? This is a to x pt dt. And this can be written as a to x p x dt. Okay. So what is this? Y minus x upon x minus a, y minus a to x px minus pt dt. Okay. But what we have, px is less than, px is greater than pt for all x belongs to, sorry, t belongs to a to x, t belongs to a to, this means px minus pt is greater than equal to 0 for all t belongs to ax. If this is greater than this integral, this is non-negative, this is non-negative, the whole will be greater than equal to 0. Okay. So what does it mean? It means g1y is greater than g1x for all y greater than x. This implies g1 is monotonically increasing. This implies g1 is function of bounded variation. Bounded variation. Similarly, we can show that, we can show G2 is function of bounded variation. Okay. Similarly, we can show G2 is function of bounded variation. So what we conclude here, this is G1, Gx is xa minus x minus a minus G1 x plus G2 x. This is minus here. G1 is function of bounded variation, G2 is function of bounded variation, and this is monotone function. This is monotone function. So it is bounded or function of bounded variation. This implies G is function of bounded variation. So which option is correct? Which option is correct? G is not function of bounded variation. This is not correct. G is unbounded. This is not correct. G is function of bounded variation. Once it is function of bounded, it is bounded. Okay. So option number B is not correct. So option number C is correct. Okay. So let's see fourth question of this set. This function is given. F is differentiable on 0, 1. You can check this is differentiable. Okay. So this is not differentiable. You correct it. You can check F is differentiable. Okay. F is not continuous, F is continuous. So first two options are not correct. F is not function of bounded variation, F is function of bounded variation. It needs to be checked. Okay. Sorry. This is not differentiable. Okay. So first option is not correct, second option is not correct, and C and D need to be checked. Okay. To take this partition, to take Pn is equal to 0, 1 upon 2n plus 1, 2 under root. Then you take 2 upon 2n minus 1, 2 upon 5, 2 upon 3, and then 1. Okay, what you will get? Then SP and F will be of this. This will be equal to this will be equal to 2 times 1 upon 3 plus 1 upon 5 this will be equal to 3 by 2, 1 by 3 plus 1 by 5, 1 upon 7, like that, 1 upon 2n plus 1, 2n minus 1, 2n minus 1 plus 2n plus 1. And this tends to, this is divergence, this tends to infinity as n tending to infinity. Okay. So what does it mean? It means this implies BF 0, 1 is infinity. So this implies F is not function of bounded variation. Okay. So which option is correct? The function is differentiable. So it is not correct. It is not correct. It is not correct. And this is correct. So B is not correct. So C is correct because it is not function of bounded variation. Okay. So see the last question of this session. Now you see this question. So what you will get? The question is similar. We need to take the partition here. You see that, first of all, this function is not differentiable. Okay. In the neighborhood, this becomes 0. Limit x tends to 0 plus f minus f0 dot x minus 0. So what is this? Limit x tends to 0 plus. So this is under root. So this becomes infinity or and sometimes oscillates. Okay. Oscillates. So this implies f is not defensible at 0. Okay. So limit does not exist. It means derivative does not exist at 0. Okay. So it means it is not defensible. So first option is not correct. Okay. F is continuous. So second option is not correct. Now we will need to check C or D. You take this partition. Take Pn is equal to then what is SP and F? That is 2 times 1 upon under root 3, 1 upon under root 5, 1 upon under root 2n minus 1 plus 1 upon 2n plus 1. And this stands to, this is divergent, it will partial sum of divergent series. So it stands to infinity as n tending to infinity. It means BF 0, 1 is infinity. This implies f is not function of bounded variation. So which option is correct? C option is correct. Okay. So today's session up to this. If you have any problem related to this session, you can comment me on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's session. Thank you very much.